Welcome back to Physics 371 Online. We're forging ahead now, having spent quite a bit of time dealing with electric fields and now recently electric fields in matter. We're going to move ahead to deal with with magnetic fields that are not dependent on time. This is the realm of magnetostatics. A brief introduction to magnetic fields reminds us that this phenomenon has been known for thousands of years through natural minerals, and mariners in the 13th century discovered the tendency of a magnetic needle to point toward the north, which we now know reveals the presence of the Earth's magnetic field. This, of course, was useful for navigational purposes. And you can see through this schematic diagram that the Earth behaves quite similar to a very large bar magnet. The magnetic field lines line up in the direction of the magnetic field at any point in space. Here's another diagram, which is actually a picture showing iron filings clinging to the regions around the north and south poles of a magnet and lining up with the magnetic field lines. And it was pictures like this that gave Faraday and others like him the notion that they could describe magnetic and electric forces in terms of fields. Here's another schematic that shows the magnetic field profile of a solenoid. The convention is that magnetic field lines emanate out from north poles and circulate around to go into south poles. And while there are many parallels between electric and magnetic fields, there are notable differences with magnetic fields. One of the things that we see in nature that is a little bit surprising to us is that magnetic fields in magnets exist only in pairs of north and south poles. You can never chop this magnet, for example, into two pieces and say that one is just a south pole and one is just a north pole. If we chop it in half, we create two new pairs of poles. Magnetic field lines, contrary to electric field lines, never begin or end. This happens because of number one, because there are no such things as magnetic monopoles. And so the field lines circulate in closed loops completely. Magnetic fields, contrary to electric fields, they're caused by moving charges, and they also only produce forces on moving charges. And finally, and somewhat surprisingly, magnetic fields do no work, and I'll show why that is in just a moment. Now let's talk about the force of magnetic fields on a moving charge or current. It's demonstrated experimentally, and this has been known ever since it was discovered in the 1820s by Oersted and then developed more by Biot, Savart, and Ampere. It was known that a magnetic field produces a force on a moving charge that has the interesting property that it's perpendicular to the plane defined by the field vector and the velocity vector. And therefore the force is perpendicular to both the field and the velocity vectors. Quantitative investigations that were done in the early 1800s showed that there's a nice compact mathematical way to express the force that a magnetic field exerts on a moving charge. So we've got the v vector here, and then the b vector indicated by the parallel yellow lines. And if this is a plus q charge, then the force is given by this expression qv cross b. And the right hand rule will tell us that you take the fingers of the right hand, extend them along the v vector, and curl them toward the palm, toward the b vector, and the thumb points in the direction of the force. Now that is if the charge is positive. If the charge is negative, then a negative sign is introduced and the force is in the opposite direction. So for this positive charge in the sketch, the force is directed out of the page. The Lorentz force law is what this equation is called, and you can see that the units of B can be expressed if we were to solve this equation for B, or just look at what units it must have. It would have units of Newton seconds per coulomb meters or kilograms per coulomb second. And in the SI system, we call this unit the Tesla. Again, reinforcing the idea according to the right-hand rule that in this case, for a positive charge, the force is out of the page. Now, I mentioned a few minutes ago that magnetic fields don't do work, which does seem kind of surprising, but we can show this in just a few lines by remembering the definition of work done by a force as the integral of F dot dl. Okay, so if we now have a moving object, a moving charge in this case, then dl can be written as the velocity vector times dt. So if we solve this for v, we would just get dl dt, which is the definition of velocity. So in a small time dt, the charge moves through a distance dl. So that gives the work as F dot v dt, if we just make the simple substitution. But wait a minute ago we just said that according to experiment and summarized in the Lorentz force law, we know that the magnetic force is perpendicular to both the b vector and the v vector. And as a result, that dot product always goes to 0. No matter what direction the charge is moving in, no matter what direction the magnetic field is moving in, this F dot v expression will always give 0 for magnetic forces. No exceptions. Now let's look at the force of a magnetic field on a one-dimensional current, and we'll extend this to talk about 2- and 3-dimensional currents in a minute. If a magnetic field exerts a force on a moving charge, and if a current is a collection of moving charges, then the field will exert a force on the entire current, or the entire object that's carrying the current. So sometimes it's useful to find an expression for this force that doesn't involve the individual charges, that's just written in terms of the current. And so let's imagine that we have a straight wire with mobile charge per unit length lambda, carrying a current I, having a length L, and it's in a uniform magnetic field B. And we can easily show that the net force on this wire is equal to the total charge Q times V cross B, the same way that it would be if we had an individual charge Q. And the total charge in the wire is charge per unit length times length, or lambda times L. And you can show that lambda times V actually has the dimensions of a current. Why is this? Well, remember, lambda is charge per unit length, velocity is length per unit time, and so therefore their product has dimensions of charge per unit time, and it's in the direction of the motion of the charge. So lambda times V becomes the current, and then I'm just going to put the L distance on the right hand side. So this force for an entire current carrying wire becomes I cross B times L. Now L, if you can also express this with L being the vector, and so you could call I just a scalar and write this as I times vector L cross B. And so in either case, the vector I or the vector L point in the direction of the current flow. More generally though, what if the wire is not straight, or if the field's not uniform? And if that's the case, all we really have to do is convert this expression for the force into an integral. And so instead of having a length L for a straight wire, we might have a path leading from one end of the wire to the other, and so we'd have to integrate over that path this quantity I cross B. And another way to write this, as I mentioned before, we can call I the scalar and then let dl carry the direction of the current, and so we can write this as I times the integral dl cross B. Remember, in this expression, dl points in the direction of the current flow. Now here's an example where we will use that equation from the previous slide to find the force on a segment of wire. So let's imagine we got a segment of wire carrying a current I, and this segment of wire is actually made up of two semicircular segments joined together. So there's a uniform magnetic field B, there's a current I flowing through this wire, and the two semicircles have radius r. What's the force on the segment? So it looks kind of complicated, and it is, but it simplifies significantly if B is uniform, if B has the same direction and magnitude everywhere in space. So we take that expression for the force from the previous slide, I times the integral dl cross b, and what we notice is that if b is uniform, right, then I can actually do the integral over dl and get what that vector is, because every term in that integral will just get crossed into b. In other words, b is not changing along the entire path of the integral. So I can write this as I times the integral dl, and I put brackets around it. That will give me a vector crossed into b. And this simplification assumes and relies on the fact that b is indeed uniform and not changing along the length of the wire. So we can write this vector in the brackets very easily. It's just the sum of the infinitesimal length vectors, starting at one end of the wire and then moving over to the other end. So it's just dl1 plus dl2 plus dl3 plus dl4, and all those vectors are connected head to tail, and so the net result is simply that the integral dl vector is a vector going from the beginning of the wire to the end of the wire in a straight line. So we'll call that vector L, and drawing it on the sketch in red shows how it's oriented. And so in this case, the force equation simplifies quite nicely. We see that L is equal to 4 times the radius in what I've called the x direction. And then the force is really simple because we just take that, the x hat direction for L, cross it into B, right? So if we take fingers along x and curl them toward B, then the force is out of the board or in the z hat direction. So that's a very nice simplification of what looked initially like it was going to be a pretty hard problem. Okay, let's consider, in wrapping up here, consider the force that a magnetic field would exert on a two-dimensional current. And of course this would have to be a current that's being carried in a sheet. You could take a piece of aluminum foil and connect it to a battery, and then the current would flow not along the length of any single wire, but it would flow throughout the sheet. So imagine that we've got a two-dimensional sheet of current that has a charge density of mobile charge carriers, in this case of electrons, sigma. Sigma is charge per unit area. So there's our sheet, and what we're going to do now in analyzing the behavior of the current and how a magnetic field affects it is we're going to imagine that the sheet is broken down into many narrow ribbons of current. And these have length L, they have width dl prime, dl perpendicular, because it's along a direction perpendicular to the current flow, and they're carrying charges at a speed v. And what we'll now do is define a new term that's called the surface current density. And this is what K represents in the sketch. The arrow indicates the direction of the charge flow. So K is defined as the derivative of the current with respect to the perpendicular direction. So it's the current per distance perpendicular to the flow. And that's indicated here. The dl perpendicular is measured perpendicular to the current flow. Alright, so to simplify that, remember that current is charge per unit time. So a differential amount of current would be a differential amount of charge divided by time, and the z hat, I'm going to call this the z hat direction, the direction of the flow. Well, dq, the amount of charge that's in that ribbon, is sigma times L times dl prime, right? Because sigma is charge per unit area, and then if L is the length of the ribbon and dl prime is the width of it, that L times dl perpendicular gives the area. So sigma times area is charge over T again, and look what happens. The dl perpendicular cancels out, leaving us with sigma L over T in the z hat direction. L over T is simply the charge velocity, v. So we've shown that K, this current per unit length, is equal to sigma times v. So in a magnetic field, the force on the sheet can be written like this. The sheet's carved up into little individual bits of charge, and so we have dq v cross b. We integrate that, and dq is equal to sigma dA, where dA is just a area element on the sheet. And finally, we see that the sigma times V can be written as K. Okay, so we've just done a little bit of bookkeeping here, and now we've expressed the force on the sheet in terms of this new quantity that we've called the surface current density. So it's the integral of K cross B dA. And finally, one last case is the case of a three-dimensional solid wire that was carrying current where the charge density for the mobile charges is rho, charge per unit volume. So imagine a cylindrical wire, and that wire being composed of many narrow tubes that each carry current through a length L, cross-sectional area dA perpendicular, with charges moving at speed v. Alright, so there's the little tube, and we're going to imagine that there is a flow from left to right of charge, the cross-sectional area being dA perpendicular, and J is what's called the volume current density. It's not current per unit volume. That's a little bit of a misnomer. We call it the volume current density because the current is distributed throughout a volume. But J is actually defined as the current per unit area perpendicular to the flow. And once again, let's just simplify this. The dI becomes dq over t in the z hat direction. Now dq, since this is a three-dimensional quantity, is equal to a charge per unit volume times a volume. L times dA perp is the volume of that tube. So rho times the volume gives us the charge in the tube over T. And once again, the dA perpendicular terms cancel out, leaving us with rho L over T in the z hat direction. L over T, well, that's just the velocity. Okay, so L over T in the z hat direction is the velocity, showing us that J, the current per unit area, can be written as rho V. And once again, we'll find the force that a uniform magnetic field would exert, actually any magnetic field would exert on this wire. We start with, once again, the integral of dq v cross b, and immediately dq becomes rho d tau. And then we see that rho v, well, that's just J. So once again, we find the integral J cross b d tau, where we're integrating over the entire volume of the wire. Now, let's compare these three force equations that we've just derived. For the case of a one-dimensional wire that carries current I, the force is the integral of I cross B dl along the length of the wire. For a surface that's carrying a current density K, the force is the integral of K cross B integrated over the area of the sheet or the surface. And finally, for a 3D solid conducting wire, the force is the integral of J cross B d tau, where the integral is over the entire volume of the wire. And look at how similar those equations are. You can see now why we go to the trouble to define these quantities K and J, because when we do, they give us a force equation very similar to the original one for the one-dimensional wire. So I, remember, is current. K is current per unit length perpendicular to the current flow, and J is current per unit area perpendicular to the current flow. We'll have some occasion to use these equations in homework problems and in our study of magnetic fields and the forces they exert. So, I'll see you in class.